And I realized that it even has some connections to Germany. Not only that Johannes Meyerhofer was German origin, but also Walid was got some of his education and interesting work in Germany, and he speaks fluently German. And now I'm the first German or the non-American to get this award. I'm very proud and very pleased, and thank you very much. When I was asked to give a lecture about our work, and it is the award is giving for lifetime work, I realized that it is exactly 50 years ago when I wrote my first publication in Tetrahedron Letters, and at that time I looked a bit different, but I used NMR. What is down here? Can you skip this? And it was, as you can see, a reaction of furane with diazomethane. And to prove the structure, we used NMR and could exclude the other structures here easily. And so I become interested. This was during my PhD work, actually in the master's thesis. And then I became interested in intramolecular mobility, because I had to measure NMR for all my colleagues and saw a lot of line broadening effects which organic chemists didn't understand at that time. And so at that time there was not much known. I cannot do anything now. This was not in my computer, which is normally also giving me some problems by making new advertising or something like that on the computer, which I don't like. Now we lose some time. I will speak a bit faster then. I'll probably skip some slides. Are you working on this or? Okay. So I did barriers of rotation in molecules or inversion, and also fast valence isomerization, ion pair recombination, for instance, which is not included correct. You can measure barriers of about 10 kilocals for this ion recombination barrier, which is mainly the different solvation of the ions and the covalent species. But at that time it was completely new. And we looked at many systems in this one. So let me now go on. And at that time, there was not much known about rotational barriers between this 3 and 20, 25 kilocals, where you can separate them. It was like the backside of the moon, which was also not known at that time. And so here you see the first fast rotation of double bonds here. This is easy to understand. This is biradicals. This is an aroxyl radical and another aroxyl radical, and you can measure the barrier about the double bond. And then I became interested also in mechanistic studies. How is an imine inverting from this form to that form? It can go by a rotation, by a polarization of the CN double bond, or by a hybridization change, which keeps the energy which you need is a promotion energy of the lone pair. And when we put on large substituents here in the ortho position, when a rotation occurs, the barrier should increase. When an inversion occurs, the barrier should decrease. And we could really prove for all substituents, also on the carbon, even if you have nitrogen on the carbon, that inversion is the right mechanism. Then also, as a peptide meeting, I will talk about peptide a bit. So here you see the normal acid analyte, which has a completely trans conformation for steric reason. You have steric hindrance. But when you substitute the ortho position again here, then the amount of trans, this is cis conformation here, is going down, and the cis conformation is populated more and more, because the increasing size of R decrease the size of this substituent. And at the same time, the barrier increases from methyl to tertiary butyl to 24. And this makes it possible that you can separate them. And we did the first separation of cis and trans isomers of peptides. Here the spectrum of the trans is shown. This is cis had only this peak. And another thing is conformation studies and ring inversions. And again, I take a peptide, which is a trisarcosyl, which has a A-B system here, and the methyl group. But when you look carefully, you see very tiny signals. And it can be impurity or another conformation. A careful inspection showed that all small singlets are in exchange with the A-B system. And I had a problem, but finally I found the solution what this is, because I realized that Danitz Vasa has already done about 10 years before a nice comparison between the conformation of cycloalkenes with cycloalkanes. If you substitute a double bond by a CH2 group, a cis double bond by a CH2 group, and all this is cyclononatrine, you end up with a chair of the cyclohexane. But there exists also a flexible boat conformation, and this is also true for the trisarcosyl. And so we could explain the small signals, and also when you have one proton can shift these, you have 6 different positions, and each single proton then can take the same position, and this equilibrium is fast. You see a singlet, and you can measure the exchange rate, and so what we did is energy profile of this interconversion. So another question at that time was, is the crystal conformation and solution conformation identical? And there was a lot of debate, and normally people believe, and this you can still now find people who they claim they have an X-ray structure, and now the conformational problem is solved, which is totally nonsense. But sometimes this is correct, but also nonsense is sometimes correct. I will give you an example. But we also determined conformation solution, conformation biological activities, and did conformational restriction, the search for bioactive conformations, the application of these restrained peptides, conformational bioavailability, and conformational interconversion, how do you control it, and so on. So 33 years ago, when we have proven that the conformation may be different. So when you take a case where, this is my coworker, a bit not at that time, I couldn't find an old picture, so the crystal conformation is not the most stable conformation, and if we search for a system which has reasonably high barriers between the two conformations. And then we dissolve the crystal at low temperature to avoid any interconversion, and then warm slowly up and see the new signals. This is an unequivocal proof for conformational exchange. And I took 2 examples. One is a Bock phenylalanine. In the crystal, we have 2 conformations, but the urethane bond is in both conformations cis. The 2 conformations of the crystal differ by having the tertiary butyl group up or down. So in the solid state NMR, you see a doubled spectrum. And then we dissolved the crystal, as I told you, and at about minus 40 degrees. And saw the spectrum of the cis conformation, and when you warm it up, you can up already at 0 degrees centigrade, you can see the trans conformation, which is the most stable in solution. The reason for that is that in the cis conformation you need intermolecular interaction, which is stronger in the crystal. Here you have a very flexible intermolecular interaction. The intramolecular hydrogen bond is predominating. So I already told you this is in principle. But this is not only on this BOC-Phe or the small molecules. You can find it's the same in cyclosporine. In chloroform, you have 96% cis of cis peptide bond and only 4% trans. In the crystal is purely cis, and in DMSO we see many conformations. We also looked at FK506, which was, and also rapamycin, which was a difficult NMR studies because you have not enough protons in the interesting range here, and it was difficult work. But in the crystal is cis, in the chloroform 2-to-1 cis to trans, and DMSO is only trans, and similar in rapamycin. When we did the cyclosporine conformation, and this was done by Hartmut Oschkenat, who is now full professor at University in Berlin, Free University, and we found that the conformation, the crystalline solution is very similar. And when we tried to publish this in JACS, it was rejected. Also, it was the first structure of a cyclic peptide based purely on NOEs and some J couplings. So we sent it to Helvetica Chemicae Acta, and it appeared the next year. You have to have in mind that at the same time, the first protein structure based on NOE from Kurt Wüthrich were submitted later than our paper, not to JACS but to JMB, and this was published the same year, in '85. So we used these NOEs very early for confirmational studies. And later on, we developed a system with Burkhard Louis, who is now professor in Karlsruhe, where we took polystyrene sticks and let it swell into NMR tube. And as a peptide chemist, we knew that resins swell a lot. And so when you swell it in the tube, then it can only extend in the large extension, so you have an orientation of the polymer. And if you put some samples in, you can see some residual dipolar coupling. And from this, you can derive structures. But when we took the crystal structure or the solution structure, the RDCs, which we determined, completely failed. It was not possible. So it was a surprise. But if we refine the molecule, we can make a good correlation. And the interesting thing is that the conformation in the crystal is a red one, the NMR base is a green one, and the refined structure is a blue one. So there is good overlay in this part, and we can also overlay the other part, but not send this part. So there's a kink in the molecule, which you cannot determine by NOEs, and also, of course, it is not available in the crystal. So this kind of detailed confirmation studies you can answer by modern technologies like RDCs. What have we done in these past times? We did a lot of novel NMR techniques. We were the first in Germany to use COSI, ROSI, NOSI, and so on, which has been developed in the Zurich group, mainly by Richard Ernst and used by Kurt Wüthrich. Extensive use of 2D NMR and new technologies, the first pulse ROSI colloq, the correlation via long-range coupling, where you can see heteronuclear long-range coupling and determining connectivities or diastereotopic assignment. You can still see people use, like in proteins when they do NMR, they make the diastereotopic assignment by looking at NOEs, and I think this is wrong, because in small molecules you can use J couplings, heteronuclear J couplings, much better. And also, when you want to determine a conformation, you have to use NOEs, and you cannot use NOEs for assignment and conformation. Then you are biased, and this is not the correct way. But most people do it now because it is done so in proteins where it is reasonable, but they use protein NMR technology for peptides, and it's going worse in the recent years. about 90% of all publications in small molecule NMR are not done correctly as we have done 20, 30 years ago. So Mexico is a measurement of fast exchanging proteins, measurement of exchange proteins. This is very often used even now in many 3D techniques and so on. And some 2D techniques, relay techniques, which were the basic of 3D NMR. My coworker, Christian Griesinger, who went then to Richard Ernst because he could not do in Frankfurt the calculation of 3D. We had a 1.5D spectrum already, and we published this as 1.5D. So we knew that if we take this relay as a new evolution period, we can have a 3D, but we couldn't calculate. This was one of the reasons I moved. I had a chair in Frankfurt for 18 years, and this was the reason I moved to Munich. Let's go to peptides. The thymopentine from the Goldstein group was looked at, and you know this pentapeptide sequence, and the NMR investigations say that the data are compatible with the assumption of high motile dynamic equilibrium between different conformations in the peptide. So we made cyclic peptides in which each of the 5 amino acids is once taken in the D configuration, and we found that this compound is now super active compared to the linear peptide, and others are non-active and so on. So this was the first case of spatial screening, and this should be a T. And Rolf Geiger was working at Höchst company, was a good friend of mine, old friend. He was like a father to me, and taught me peptide chemistry also, because when I came to Frankfurt and took the chair of Theodor Wieland, the well-known peptide chemist, I had no idea what a peptide is really. And so he said, why not using spatial screening to RGD peptides? And I thought, we have proven the principle for one case, why should I do another one? But then I moved to Munich and had more co-workers, and then I had to take some more topics, and so I choose these topics. And you know that integrins are very important molecules, called cell adhesion. They are involved in angiogenesis. Here you see the activated integrin. In the non-activated states, transmembrane regions are crossing each other. We also have recently published something about that. And there is a kinked version. And it is important for embryogenesis, cell adhesion, of course, and also in some illnesses like cancer, blood coagulation, thrombosis, and so on. So there are 24 heterodimers, and it was a big advantage and a big discovery that when Erkki Ruoslahti discovered that some of the integrins, in the beginning he thought all integrins like recognize RGD, but some of them are really recognizing nice music. Okay, but there are these are the RGD recognizing integrins, and you see that some of them are involved in the platelet aggregation, others are in cancer, and there are a number of different alpha and beta subunits. For instance, the beta 3 subunit is involved in this platelet integrin and also in this cancer integrin. And if you look for the RGD sequence for different integrins, they are all in this extracellular matrix proteins. The question is, where comes the specificity from? Normally, biochemists think, oh, there are additional binding sites. But we ask the question, is the conformation important also? And so when you see the RGD peptide is very flexible, and you have a lot of different conformations. And then when we looked at the structures which has been determined from RGD-containing proteins, it turns out that you cannot rely on this. Either there are X-ray structures which are outside and they can be switched, and also that are not well defined. So what our model is the following: when we have a flexible molecule in which bioactive conformation is only partially populated, then if we rigidify the molecule, then this molecule is now superactive in a matched case, but if you do it wrong, it is does not fit at all. But the big question is how to find the right conformation. If you, for a moment, assume that this is a two-dimensional representation of a conformational space, there are some receptor subtypes which recognize one conformation, another one, or another one. And normally, different subtypes recognize different conformations or slightly different conformations, in addition to different binding sites. But if we now restrict the conformation by to this space, we get a selective but not very active compound. Here we get a biselective compound, very active. And in 95%, the cyclic compound is not active anymore. So to search for the best conformation, we had the following idea. When you have 5 times the same amino acid, like phenylalanine or glycine or something like that, or alanines, then you have a rapid equilibration of 5 different conformations if you assume that one, let us say, a hydrogen bond is determining the conformation. And then you observe an effective C5 symmetry. Also, the individual molecule is not C5. But if you disturb the symmetry, then it might be that you find one preferred conformation. Of course, equilibration, you have different ground states, different excited states, but you can, if you are lucky, you find a preferred conformation. And this is what we are looking for. And in that case, we use the library approach, but we look for the preferred conformation. It is not a rigid conformation. It's often claimed a rigid, but it's not rigid. So we started with a simple molecule again, with alanine. When you have 1 or 2 or 3 alanines, these are all possible penta and hexapeptides with D and L alanines. There are no more possible. If you have 3 D residues here, then this is a mirror image of this, so we cannot differentiate in NMR. But we also played a bit more by putting on glycine and D and L proline in the system, and then looked for preferred conformation. And in that case, we found that this one, 1D and 4L, occupies a preferred conformation, which is now very well known. It is the D amino acid occupies a I+1 of a beta-2' turn. And then we can do the following. We are looking for the best spatial arrangement of the RGD sequence. So we looked in the data bank and found that proteins, extracellular matrix proteins, show very often that they are flanked by valine and phenylalanine. And so we put on an X, and they have hexapeptides and pentapeptides, and synthesize the libraries of these compounds. And I will show only the pentapeptides. You see in the upper left corner is always a D amino acid, D-phenylalanine, D-valine, D-arginine. Glycine can also occupy a D position, and the D-aspartic acid. So you have always the same conformation, and this was also proven by NMR. But you see that the activity compared to the linear GRGDBSK, which was a reference compound, and you see that we achieve here a compound which is 1,000 times more active than the linear peptide. This is 100 times more, this is less active, this is 10 times more, this is less active. So just by this simple procedure, we have identified the first selective and superactive compound. Selectivity means that it does not bind to the alpha-2b beta-3 against fibrinogen. This is a natural receptor for alpha-2b beta-3. And the IC50 for this linear peptide is about 1 micromolar also. But here we find much less activity. So we have increased at the same time the selectivity by a factor of 10 to the 4th. And then to make a long story short, we have a linear peptide which, when the extended conformation is mainly selective for alpha 2b beta 3, and when it is kinked, has a preferred conformation for alpha v beta 3. And this is important for cancer. And then we played a lot with different molecules, and one peptidomimetics was N-methylation, which was done by my co-worker Michael Dechansreiter, and he N-methylated every amide bond, and in that compound he found a compound which is 4 times more active than the parent compound, and this compound was then selected by Merck, which we collaborated since 1991 or 1992. In this field, they also synthesized RGD compounds, but our compound was fortunately better, but unfortunately it was not so good. Then this zilenkitide failed after 5 years in clinical phase 3 for efficacy against gliomas. So the reason is not clear, but I think the testing was not done very carefully. I would do the first by making images to see if the molecule can cross the blood-brain barrier, which is often not well working in glioblastomas. But they treated all patients, and then they could not prove efficacy. If Horst had done the same for Gleevec, it would never come to the market. And at that time they failed, but it is still now in several phase 2 or phase 3 studies in other cancers. But we did a lot of different modifications like thiopeptides or reduced peptides, peptoids and sugar amino acids. I will give you one example, which we introduced about 20 years ago, sugar residue with an amino group and a carboxyl group. Then you can have a fixed conformation of the carboxyl group and the amino group. The stereochemistry is well controlled, and you have a good water solubility, which is often the problem of peptides. But we are not more working in this field. There are several other groups now doing sugar amino acids. But here we found that the valine can be substituted by any other amino acid. And so we can use it for different applications. And we always use this stem peptide because Merck asked us not to work with zilenkitide, not to interfere with the development. Then we linked some radionuclei to, for instance, developed galacto-RGD, you will see in a minute. We also used it for biophysical studies and also for coating bone implants. I will give you some examples now. The activity is very high, selective for alpha V beta 3. It has also, the zilenkitide has also some activity for beta 5, alpha V beta 5. And it was, and is still not yet known completely what the different endocrines are important for the different processes. Okay, let's go on. We want to use selective radioligand for tumor matter to identify tumors. And our first ligand was working, but it did not show, it was also going into thyroid and some other organs. The disadvantage is that the endocrine ligand binding is mainly polar. We have this arginine and the carboxyl group, so it is a high off rate, and so it is washed out very rapidly from the receptors. So we tried many modifications. Only one was successful, and it was the sugar residue in the lysine position. We put a lysine in here, and then we made sugar, and here we used for SPECT, the iodine 125, or here we used so-called galacto-RGD with a fluorine 18 labeling for PET. And PET is certainly the best technique and very, very good resolution. Here you see the tumor in the mice. This is blocking studies when you treat it with soluble peptide before, and here is a blocking experiment. Excuse me. This is an experiment with a cell line tumor which does not express alpha V beta 3. And this is also done in men. In Klinikum rechts der ISA, they have hundreds of patients looked at this. You can here see a PET picture with galacto-RGD, the overlay with a computer tomogram, and you see what the doctor has to remove. And when he removed this axillary lymph node metastasis, you see that it is immune staining. It is very active alpha V beta 3. Now coming to the bone coating of biomaterials. Normally, the critical issue between implants and the surrounding tissue is a connection between the two different materials, and the osteoblast adhesion occurs via RGD sequences. So what we developed, different anchor groups for different materials like PMMA, titanium, or serum albumin, or gold, or other lipids for membranes. Different peptides, cyclic peptides and peptidomimetics. I will talk about this later. And different anchors and anchors to these groups, which can selectively address the different materials. In the beginning, we found that in PMMA, not coated, you can almost find no cell adhesion, and these are not spreading the cells. You can wash them after a few hours, wash them away. Whereas when it is coated, you can see they are proliferating and also attaching. And here is a rapid, very early testing in 2000, 13 years ago. You see that if you have a hole in your bone and you fill it with granulate, then it is normally surrounded by collagen and fibrous tissue, so that the bone cells, osteoblasts, cannot grow into. But when the polymer is coated, you see that the blue bone is already formed here, and this brown is not the same brown as here. It is, they will turn also blue. This is osteogenic material. Very recently, we did a different things. You know, restenosis is one of the big problems in stents. And normally people are doing, not using bare metal stents anymore. They are coated with some toxic materials like cyclosporin, rapamycin, and sirolimus is now called in medicine. And we have attached to this the RGD binding peptides to attach endothelial cells. And this was very well working, because in the beginning the very rapidly smooth surface is formed, and the smooth surface is good for prevention of restenosis. But later on, and this is just sent in, is not yet published, I hope it will be accepted. We used lipophilic residues here, like this ones in different, and finally we ended up with this naphthalene compound. And you can see here that when we have an normally RGD-eluting stents, with our compound, you see the thickness of the new blood vessel is nice. If you have the bare metal stents with the toxic, no, this is bare metal stents, this induce a lot of intima growth into this, and this is not good. This will cause restenosis, and with coated of sirolimus, it is not very active. It is killing all, not only the smooth muscle cells, which are the bad guys. The good guys are the endothelial cells. You want to attach endothelial cells and to avoid binding of the bad guys, the smooth muscle cells. And this is what we are trying. Okay, we also did quantum dots early together with Andreas Bausch. Here he used quantum dots, and then he streptavidin and coating with our peptide. And then he looked at the bound nanodots on the living cells, and he found that there are 3 different mobilities. Some of the nanodots stay completely fixed. Others are turning around in a large area, and third class is binding sometimes here, and then it is moving around. And you can all classify these different mobilities, and this has to be is connected to the formation of focal adhesion from the in the integrin binding of a cell. The first step is binding single integrins, and then the integrin aggregates. I think the beta subunit forms homotrimers, and then the alpha subunit you can have a tripod interaction, and then these aggregates further, and then you find the multiple valence stable connection. You can use RGD peptides for targeting to different cells. We recently wrote a review in this frontier of pharmacology of anti-cancer drugs. With MG-Fin, it's Scripps, we coded his virus-like particles, and you can see that these specific positions can be monitored by a complex process. We use click chemistry, of course, with MG-Fin, and the cyclic peptide, and then also some fluorescence labeling. And you can see that these particles are internalized. Is carefully studied that they are internalized, and this stimulates internalization. And the final idea is to put drugs into these virus-like particles to select the cancers. Now some physical chemical studies which were done together with Joachim Spatz. He has a group in the Max Planck Institute in Stuttgart and also in Heidelberg, and he is able to design hexagonal packed gold dots on surfaces. The trick is the following: he has dipyridyl residues, and then a long aliphatic chain, and then he reduce gold salts, and then you have the gold dot inside, and then if he irradiates this with plasma, also organic material is burned, and the gold dots stay on this, and so the length of the aliphatic side chain determines the distance, so we can change the distance between 20 and 120 nanometers. And then the surface is passivated, and our RGD is bound there, and then we can study the cells. And here you see when the glass plate is not covered, you see no adhesion. When you have only the gold dots, or the gold dots in large space, they are not really spreading. The cells are staying not long on this position. They are exchanging fast, but if the distance is smaller than 65 nanometers, they extend and are spreading, and this is a good sign for cell adhesion. That is not only the total number of integrins which is important, it is the arrangement. So what Joachim did is he designed a micro array in which he has nano dots here, in which he has this spacing is 58 nanometer spacing, which is sufficient for binding, but he has nothing, no gold dots, not here and here. And then the overall density of gold dots on this whole plate is less than it would bind. But here you can clearly see that it binds to all these planes, and so it needs some clustering of integrins, and if you look carefully and pull on the cells, you can see that each integrin is really binding to the different gold dots. about 10 years ago, we found that the limitation for endocrine subtypes investigation is that with cyclic RGD peptides, we cannot get the selectivity between the two endocrines, alpha V beta 3 and alpha 5 beta 1. It has some selectivity, but not sufficient to study the different endocrines. So we turned to peptidomimetics. At that time, 10 years ago, the first structure of an endocrine head group came out with our zilenketide, and it binds like it was expected. It's very similar, the bound conformation is very similar to the solution conformation, which we published before this conformation was done. But when we recently did a crystal structure of zilenketide itself, and the crystal structure is certainly different here, and this is an important difference because this amide bond is taking part in the binding to the receptor. So if you, and the reason for this different conformation is the stabilizing of the peptides like Reza Ghadiri has found in these nanotubes. And so in the crystal packing forms an order which is not present in solution anymore. Here you see that the solution conformation is very, very nice. And this allows us now to also to study our peptidomimetics, so you can take off the peptide and take some of our endocrine ligands and mimetics and see how it binds. And then we looked if we can use this for cell adhesion of osteoblast. And when we found two positions which should be possible, you see when we have the peptide, this is a magenta with increasing concentration of peptides, you get more osteoblast adhesion. But with this, also with the blue and light blue peptidomimetics, you can also find adhesion, but when you attach it on this side, it is not working. And this was the first specific cell adhesion of small molecules ever. So what we are doing then for other endocrines, we had Luciana Marinelli as 3 years postdoc in my group, and she's specialized in computer modeling. So we are docking designs and combinatorial synthesis and going back. And she has prepared a homology model of alpha 5 beta 1 and also alpha V beta 5. So we use these homology models to get some idea what we can do. And one example here is shown when we have the alpha V beta 5 is a white receptor, and the alpha V beta 3 is a gray receptor. You see that the molecule fits very well in the gray receptor, but it gives a clash here. So the activity drops down just by this substitution. So we understand a bit more about the behavior of the different endocrine ligands which we have designed. Another example is to differentiate between alpha V beta 3 and alpha 5 beta 1. When you compare this, the red receptor is alpha V beta 3, this is here, and the gray receptor is the background. What you can really see is that if you substitute an amide bond by an sulfonamide, then you have a twist of the peptide bond. The peptide bond is planar, the sulfonamide is 90-degree twisted. So you can get selectivity, and I have to mention that, of course, sulfonamide is not a good isosteric substitution of carboxamide. Medicinal chemist has to be aware of this. Here you see that from the carboxamide to the sulfonamide, you see that we switch completely from selectivity for alpha 5 beta 1 to alpha V beta 3 just by changing these residues. A bit other substitutions also there. This is substitution for the arginine. we achieved later on better selectivity. Here you see that we have now good selectivity between the alpha V beta 5 and alpha 5 beta 1 and alpha V beta 3. And the same is true the other way around. Selectivity is not so good, but it is quite good. Important here is a methoxyl group. Without the methoxyl group, solubility is not good, and also the activity is much lower. So it was a crucial point to improve the activity by at least a factor of 10, and also you can work with this compound, whereas without it. And I got the idea from Hartmann at Merck, who has done 15 years ago such a methoxyl pyridine. And of course, the medicinal chemistry knows this all, but as organic chemistry, you normally do not take this into account. So if we link now on this position, you see that with a larger substitution, you do not change the selectivity, and the activity is even better here, and selectivity better than here, or at least the same. And the same is true also here. We lose some of the activity, but not much. By linking it to a sulfide, and of course this is going for selective adhesion to gold dots. And here you see when we coat these gold dots by this alpha V beta 3 selective thiols, cells who are only expressing alpha V integrins adhere, whereas beta 1 expressing cells do not adhere. I must say the cells have been created by Reinhard Kessler in the Max Planck Institute and Martin Ried in Munich, and it was a 6 years work to make the flock system working and to get mice with good reproducible and cells of this reproducible system. And it's the counter proof is when you have a alpha 5 beta 1 selective thiol, you can adhere these beta 1 expressing cells, but not the alpha V expressing cells. So we have complete selectivity for cell adhesion. And also we can use different anchor systems. For instance, for titanium, we use this tetraphosphonate. When you put an implant material, a titanium hip implant, into this solution, it sticks and you cannot wash it up with acids at up to 80 degrees. You can sterilize, and it's very, very nice and completely fixed. And here we use a polyproline helix, I yesterday mentioned in a discussion, and connected this by click chemistry, but this is normal chemistry, I'm not talking about this. But we use it for binding to titanium. Titanium is normally the surface is oxidized. And so we have, unfortunately, also different colored does not appear here. It's not. I realize, and also some shifts occurred here. I don't know why. I checked it last night, even the slides. So, but here we have 4 different planes. One is has alpha V beta 3. Others have only pegylation, which is passivation for cell adhesion. And here we have a gold titanium service, and here only the titanium service with alpha 5 beta 1. And you can see that this titanium service also. So here we adhere the alpha 5 beta 1 carrying cells. They do not adhere here, and when you have passivated, there's no way. When you have this behavior, you can wash off the cells after some time. If they are not spreading, they are killed themselves by apoptosis and so on. But then you can use also some materials by having materials, gold strips and titanium or iron oxide, and then we can bind either by a sulfide linker to the gold and to the other side, and then you can see that we can selectively bind the integrins on micro or nano coded surfaces. Another interesting thing is when you takes the same cells on different integrin receptors, the shape, the whole morphology of the cells is different when you bind it to the ligand for alpha V beta 3 than when you bind it to alpha 5 beta 1. So you can see morphology changes which we are now investigating to have so the same cells behave differently on binding to different integrins, and it is not yet known which cells do which, and they can all behave. So there's a lot different things to study. Another way is when you make cross-link PEG sticks, then you can cross-linking it by light, and you have the PEG molecules in here, the solution, and then you can polymerize it here on these sticks, and then you wash off the soluble PEG, and then you have these pillars. And if you have gold dots on this pillar, and you have the gold dots are coated with an sulfur containing a long alkyl chain, the gold dots are staying when you put off the glass plate. The gold dots are staying on the tip of these pillars, and here you see that they are still here. This is the tip of the pillar, and now you can adhere cells on these pillars, and by force microscopy you can determine the strength of the pillars, how strong they are, and you can see that the cells, when they adhere, they pull the pillars in the direction of the cell and adhere to different forces. And here you can see that the alpha V beta 3 normally have different forces than the alpha 5 beta 1. So it is some interesting stuff which is not yet completely understood. Now, tumor imaging. For that, we functionalized our peptides with Nodaga, which is better than DOTA, especially for gallium-68. DOTA is more difficult to label, and it is not stable enough. And you have most people use DOTA, but those are experienced in the last 1 or 2 years. They all use Nodaga, which is better ligand and very stable and nice to label. So when we label this compound, and again we use this position which came out of the modeling from the receptor-bound conformation in the integrins, and then we saw this should be free, and then we attach the Nodaga here, and you see that we do not change the activity and selectivity, and the same is true for the other ligand. You see again the methoxyl group we lose quite only a factor of 2 maximum for activity, but also selectivity is retained. So we have 2 different molecules which can detect in PET either the alpha 5 beta 1 or alpha V beta 3. And we had a mouse in which there's 2 tumors. One has a tumor of alpha V beta 3 here, and you see we can detect the tumor by this ligand here. And for the other side, this tumor has expressing alpha 5 beta 1, and we can differentiate between the 2 tumors in the same as here. You see some crosstalk also for the alpha V beta 3, but this is clearly showing that this tumor is alpha 5 beta 1 tumor. This is the first picture of this tumor, and of course the tendency is to use this for development personalized medicine. Finally, I will give you a short interlude before I come to the end. We are using also for ligands for the chemokine receptor CXCR4, which is a GPCR. And Fuji in Japan has done a very nice work. He identified from the polyphenosine by an ALA-scan the important amino acids which are indicated in red, and put them into a cyclic pentapeptide. and then made the spatial screening. He was inspired by us and was also citing us, and he found a compound which was very active for nanomolars, and we want to use it for imaging. But any position, and this is difficult also in peptidomimetics, it's very difficult sometimes to find the right position without affecting selectivity and activity. But here, after long work, Oliver Demmer found that we can use, and this was 3 years ago, we still use DOTA, we can use this with different spacers. He synthesized more than 100 compounds to find this ornithine substituted without losing too much. In fact, we even have the same activity. But then this is a collaboration with Hans-Jürgen Wester and his group. And here you see the importance of the influence of the metal ion. If you use no metal, the activity is 150 nanomoles. With indium is 44, and with gallium 5 nanomoles. And it is important for imaging to use ligands, in my opinion, which has at least lower than 10 nanomoles. You can make pictures also with lower affinity, but you can never use it in man. Or it is useless just to make a nice picture in a publication, but this has no relevance. So you have to go for higher activity. Here you see the time evolution. The red is a tumor. After a while, the red stays stays here, and you see this tumor. It's clear, and you can, of course, block it, the study. And this is also always to be done, to a blocking study, so to prove the affinity. And here the blocking was done with a ligand which is already in clinical approved. And this is the first picture of a man. We have now more. It's not yet published. Unfortunately, this man has a lot of cancer metastasis and in the lymph, and it was a pancreatic cancer or everywhere in the body. He has metastasis, so he has no good chance to survive. And but we have now quite a few nice pictures and can use it in medicine. Now, from imaging back to drug research, the CXCR4 ligand is also used like CCR5, the chemokine receptors, as a co-receptor when the HIV entry via this CD4 molecule is anchoring to a lymphocyte. And then if you block this interaction, you can prevent normally the resistant strains of HIV to enter. And there is already a drug in development, or maybe even on the market, which is going to the CR5 chemokine receptor, which is about 60% of all resistant HIV strains. But there's nothing known about CCR4. When we looked at the conformation of this peptide, where we have the N-methyl ornithine here, and we used it for the development of the imaging. Then we realized that it might be good, like in the somatostatin case. Maybe you remember the old work of Weber and Hirschman, where they found that the lysine and the tryptophan should be close to each other, and we thought it might be similar here to here, and so we did a simple trick. We shifted the ornithine side chain to the nitrogen and make a peptide out of this. And this compound has only one conformation, and the conformation is very active, as you can see here. It is a bit difficult to realize the R1 and R2 are the alanine substitution next to the peptoid structure, and you see here that when we have a glycine, the activity is low. If we have an alanine in the right position, it is subnanomolar. If we have it in the enantiomeric position, we lose activity. So it is important to have this, the D-alanine here. And then we, of course, use different lengths of the spacer in the ornithine case. And then also optimize this. And finally, we put on the lysine into arginine, because the original receptor ligand is arginine. But it was just ornithine was done for the anchoring to radionuclei. And so we achieved to get a molecule which is 40 picomolar now. And this is by far the most active compound, much more than CMT 3100 is much less active. And it was tested for resistant strains, and you see these are HIV viruses which use CXCR4 as a co-receptor. These are the red ones. And the blue ones use a CCR5 chemokine receptor. You see that all our compounds have no affinity or no effect on the CCR5 using HIV strains. But for those who use the CCR4, we get, with our best compound, we get very good activity, and it has 29 nanomolars. You see here that all compounds in the low nanomolar range, and this is a AMD 3100, which is in development by Pharmacophore, so in a company in Switzerland. So this is my final last slide, not the final slide, it's one of the last slides. What we are doing normally is improvement of ligand technology in the imaging technology, and the radio work is done in the clinics, rechts der ISA. In the case of CXCR4 by the Wester group, he's doing the labeling and the biological studies, and in the endocrine field is done with Marco Schweiger, also in the Klinikum rechts der ISA, the nuclear resonance imaging. What I have shown you, that there's a big play between drug design, biomaterials, and imaging, and we have connections to industry, to polymer chemists, physicists, orthopedia, and medicine, of course. And a lot of collaboration were involved in this work, and we could not do everything. But it was always fun to work with others together, and so I have to thank all my co-workers and also the other groups which has participated in our studies. Just to give you a hint what we are also doing or have been done in the last years, I was heavily engaged also in NMR work of proteins, and one of the most interesting study was the spider silk work. We found that how a spider can store a protein under very high concentration, which is about 30–40%, and without aggregation, and form a silk thread within part of a second, which is 5 times more stable than steel. So, and we found a clue because the C-terminal domain is folded and is reacting with a different salt concentration, and then the partial defolding makes a switch from and gives the final orientation of the strands. And the N-terminal domain is important for multivalent N-terminal attachment, which is important for having this high stability. There's no organic polymer known which has, from the polymeric length, again, a multivalent connection to all the others. You know that many polymers have interaction between the polymer chain, like also the spider silk, but the ends are free and not linked. But in the spider has found a way to link them, because they form heterodimers, head-to-tail dimers, which are not possible when they are in the storage. They are on the surface of micelle. Also, negative charges are outside, so the micelles have high stability, cannot interact, and also the N-terminal domains cannot interact. And this was an interesting story. Also, we studied p53 interacting with HSP90, which is HSP90 has 180 kilodalton and is a homodimer. It is very big NMR. We studied the different domains and found everybody assumed that p53 is binding to the middle domain. It is in fact binding, but very low. But we found that it is much higher binding to the C-terminal domain, which was never considered, and we found also a sequence, peptide sequence, which makes this stabilization. And so the stabilization of p53, which is very important in cancer and so on, in living organisms, is first it binds strongly here with about 2 micromole. But this binding is about 89 micromole, and then it is in equilibrium, and then from here it is released to the where it has to go, maybe to the BCLX, which we also studied, and this is a mitochondrial activity of p53, or it goes into the nucleus to form this transcription factor activity. And another point which was already mentioned in the introduction was this orally available peptide by multiple N-methylation. You have mentioned the Jack's paper, and we are now trying to reintroduce substituents and working on this. If we fail, then we fail, but it is worth a try to reintroduce to make this stable. So I would like to thank my co-workers and thank you all for listening to me. I think my time is over, and I want to thank you.